Hi everyone, my name is Roman Baron, and I'm one of the maintainers of Kai Scheduler and a senior software engineer at NVIDIA. At the previous KubeCon event, we open sourced the Run AI scheduler under its new name, Kai Scheduler. Kai is a Kubernetes native scheduling framework optimized for AI workloads. Today, I will talk about topology-aware scheduling, explain the challenges it introduces, and show how Kai addresses them. Topology-aware scheduling is gaining significant traction lately. The demand is driven by rapid evolution of compute and network architectures and new emerging requirements of modern AI workloads. I will start by outlining the core challenges introduced by this evolution. Unlike in the past, modern AI workloads are no longer bound to a single GPU node. They are deployed as distributed workloads composed of multiple pods and often span over several GPU nodes. Let's consider a simple example of a distributed workload with 4 pods to illustrate why a straightforward scheduling approach might be insufficient. Without further information about the cluster, the scheduler places the 4 pods on nodes that satisfy their resource requirements. For example, let's assume that scheduler chooses nodes 1 to 4 for the workload pods. And resource-wise, it seems like a good decision. However, these nodes may not reside within the same rack, featuring high-speed interconnects like NVL72, or within the same block, or the same availability zone, resulting with different network bandwidth between different parts of the cluster. In this example, the 4 nodes on the left side are located in one rack, and the 4 nodes on the right side are located in a different rack. Within each rack, there is a high-speed network connectivity, while between the racks, the network bandwidth is more limited. By taking this information into account, the scheduler can place the pods in the same rack for optimal performance. But it doesn't end here, because it is also possible that the pods have a very specific communication pattern, and not all of them communicate with each other. Pods in one rack may communicate with pods in another, but not with those in the same rack. In this example, communication occurs between 2 distinct pairs of pods, and within each pair, the pods have been placed in separate racks. And as we saw earlier, this result is suboptimal. Packing all the pods into a single rack is not always the best strategy, and not always possible either. By analyzing the workload's communication patterns, the scheduler can determine that tight proximity across all pods is not always required. The most effective scheduling strategy emerges when the scheduler aligns workload's communication requirements with awareness of the underlying cluster network topology. For this type of workload, ignoring topology information can significantly increase latency and reduce workload throughput, and even degrade resource utilization in the cluster. You might think that Kubernetes already solves this problem with pod affinity. But in fact, it falls short due to its pod-by-pod architecture design. Let's quickly explain that. Consider a different scenario where node number 5 is already occupied by another workload. The first pod is scheduled without taking into account for the entire workload. It anchors the placement for other pods that will be scheduled next. One by one, the scheduler attempts to place the other pods in a proximate location. But since the scheduler didn't plan ahead for the entire workload, it cannot guarantee the optimal solution. In this example, by planning ahead for the entire workload, the scheduler can place the pods in a single rack on the right side. I presented a very simplified example, but it illustrates the challenges of scheduling modern AI workloads, such as disaggregated inference pipeline. I would like to continue by explaining this specific use case. This type of workload also contains multiple pods that are scheduled as a single unit. However, different pods belong to different groups, and each group is assigned with a specific role. Prefill initializes the model's internal state by processing the input prompt, preparing the context for efficient token generation. Decode generates the output tokens based on the prefilled context, producing the final model response. It is also very common to see additional supporting pods like front-end or monitoring as well. This type of workload has a very specific communication pattern. Leader and worker pods of the same group rely on high bandwidth and low latency communication to sustain model parallelism, making it the primary network requirement. On the other hand, KV cache transfers between prefill and decode groups plays a secondary but still a meaningful role. A naive scheduling strategy that only considers resource availability might spread the pods in the cluster. You can see that pods with frequent network communication between them are spread across racks and even across different zones. And they cannot benefit from fast inter-rack communication. Kai takes into account the inner workload composition of the different pods and their specific network proximity requirements. By doing so, Kai can optimally place the pods from the same group in a single rack. And additionally, Kai can take into account cross-group topology constraints when searching for optimal placement. This can be useful for efficient collocation of prefill and decode groups for faster KV cache transfer. It can be seen now that prefill and decode groups are located in a single rack, and together they are placed within a single zone. With this scheduling decision, the workload can fully leverage the fastest network bandwidth in the cluster. I would like to take this opportunity to call for action. Those who are interested in taking part can reach out through our GitHub repository or on Kai Scheduler Slack channel on CNCF Workspace. We also host bi-weeklies and maintain a mailing list for ongoing updates. Thank you.
Thank you, Roman. We can take questions for this in the hallway here.
Already gave it back. Okay. So the question was about the relationship between Kai and Dynamo. I think that it is very important to understand first that the roles are different, right? Dynamo does one thing and Kai is a scheduler. Dynamo workloads are managed with the Grove workload manager, which is scheduled by Kai. So it's a complete inference stack with all the different components, but they do different things, right? Kai is the scheduler of Dynamo, basically.